Let's jump right into this explainer. We are literally witnessing a massive architectural shift in artificial intelligence right now. We're moving away from that basic static word prediction, just spitting out text, and entering this wild new era of deterministic, autonomous task execution. Today, we're going to break down the core loop of AI agents. This isn't just about sending a prompt and twiddling your thumbs waiting for a response. It's about systems that can independently sense their environment, make decisions, actually invoke external tools, and course correct on the fly. So let's unpack the exact mechanics of how a static language model transforms into a dynamic digital worker. To start, we really have to ask the ultimate question. How do AI agents actually work under the hood? I mean, when you see an AI successfully research a complex topic, scrape a website, and then book a flight all in one go, it almost feels like magic, right? But it's entirely the result of a highly structured, logical architecture. What transforms a standard model into an actual agent isn't just stuffing it with more parameters. It's a meticulously designed sequence of operations that allows the model to step out of its isolated little sandbox and interact with the digital world dynamically.
What's really interesting here is comparing a single LLM call against an AI agent. The fundamental difference basically boils down to statefulness versus statelessness. Think about a traditional LLM interaction. You send a prompt, the model probabilistically guesses the next sequence of words based on its training data, and boom, it returns an answer. It's a stateless, one-and-done transaction. It literally has no memory of what it just did unless you manually feed it back to it. An AI agent, on the other hand, operates on a continuous, stateful cycle. It chains multiple discrete steps together, holding on to a persistent working memory over time to handle tasks that require actual, sustained computational legwork.
Step 1. Perceive and contextualize. The journey of an agent always begins with building its working context. Before taking a single action, the agent has to construct its reality. Technically speaking, this involves loading up a massive system prompt, scanning the available function signatures, which, by the way, are basically just the blueprints of the tools it has permission to use, and ingesting the current state of the environment. It pulls in your overarching goal, looks at any past conversation history, and evaluates its memory banks. This ingestion phase is absolutely crucial because this exact working context forms the foundation for literally every computational decision that follows. Step 2 is reason and plan. Now we enter the brain of the loop. With the context fully loaded, the agent applies task decomposition to your goal. It recognizes that a complex request just cannot be resolved in a single computational leap. So it breaks that primary objective down into a series of manageable, actionable subtasks. Depending on the architecture, it might map these out as a complex network of dependent steps, where task B absolutely cannot start until task A is finished, or maybe it just generates a strict linear checklist. Formulating the strategic roadmap and deciding exactly what to execute next, that is the true hallmark of agentic autonomy. This internal strategy relies heavily on a process called chain-of-thought reasoning. By explicitly forcing the model to generate intermediate steps before it actually outputs a final action, it's essentially buying itself compute time to process logic. It's kind of like it's talking to itself, laying out dependencies, saying, okay, first I need to retrieve data A so I can analyze variable B, which will finally let me execute command C. This is incredibly powerful. Outputting these step-by-step rationalizations drastically cuts down on the chance of the model hallucinating wild guesses and grounds its actions in a highly structured, logical sequence. Step 3. Act, specifically calling tools. Look, reasoning is essential, but compute cycles spent just thinking don't actually alter the external world. That brings us to the action phase, technically known as function calling. This is the hands of the agent, where it reaches out beyond its own internal neural network. It takes that logical plan it just formulated and crosses the boundary from internal processing to external execution in the live digital environment. It dynamically picks the right tool from its predefined list and generates the exact JSON or code parameters needed to trigger it. And look at the sheer breadth of tools it can use: searching the web, running code, reading or writing files, calling APIs, querying databases. Depending on the parameters set during the reasoning phase, the agent might instantly spin up a secure Python environment to crunch a massive data set. Or if the task requires real-time information, it might hit an external API to grab live flight data, execute a SQL query to extract customer records, or simply do a targeted web search. These function calls are the digital hands of the system, giving the agent the immense power to manipulate files and pull data exactly like a human engineer would. Step 4. Observe results. Immediately after acting, the agent uses its eyes. It has to evaluate the outcome of what it just did. The mechanism here is actually beautifully direct. The raw output generated by that API call or Python script is appended directly back into the agent's context window. It doesn't just blindly assume its command executed flawlessly. If it ran a script, it parses the output. If a server responded, it ingests the payload. By feeding these concrete external results back into its own memory, the agent continuously updates its internal state and refines its understanding of where it stands with the overall objective. Step 5 is loop until done. So the crucial point here is this self-evaluation phase. The agent literally asks itself, is the goal accomplished? It compares its updated context against the original goal to determine if the task is finished and loops back through the cycle if more work is needed. Interestingly, this loop is exactly why developers have to set strict termination conditions or max iteration limits. Actually, without those constraints, an overly determined agent might get stuck in an infinite loop, endlessly scouring the web for an answer that doesn't exist, burning through API credits just trying to fulfill a slightly ambiguous prompt. But when properly constrained, this looping architecture is what makes recovering from errors along the way possible. It makes the system incredibly resilient. Let's say the agent attempts to run a Python script, but it throws a syntax error. Well, a traditional static script would instantly crash and halt, right? But an autonomous agent simply observes the error. It literally reads its own traceback, realizes, oops, I missed a comma on line 4, rewrites the code block, and executes it again. Because it continuously re-reasons based on new observations, it dynamically adjusts its strategy, finding creative workarounds to roadblocks in real time. Step 6, return response. Once the agent verifies that all subtasks are complete and the primary objective is met, it exits the loop and finally delivers its completed answer to you. What's really remarkable about this phase is the sheer level of abstraction it provides. From your perspective as the user, you just submitted a prompt and received a polished, accurate answer a few seconds later. You are completely blind to the furious cyclical problem-solving, the multiple API calls, the Python debugging, and the persistent error correction that was firing off in the background to make that answer possible. Let's quickly review this chronological journey: perceive, reason, act, observe, loop, and return response. This entire life cycle happens in a continuous, recursive loop. It's just an incredibly elegant, continuous cycle of perceiving the environment, reasoning through complex dependencies, acting upon the digital world, and observing the consequences. Synthesizing these discrete steps into a unified architecture is precisely what transforms a passive language model into a highly active problem-solving engine. There's a great quote here. Agents differ from a single LLM call by having this sense, think, act, observe loop. This really encapsulates the core insight perfectly. The true power of these systems lies in this exact progression. This framework elevates an AI model from a simple text generation tool into a highly capable digital worker. By operating within this dynamic, self-correcting cycle, a static intelligence becomes a proactive participant in the digital ecosystem, completely capable of sustained, independent effort over time to achieve concrete, complex objectives. Which leads us to a pretty massive question. With the ability to sense, think, act, and observe, what complex problems will these autonomous workers solve next? As we wrap up this explainer, consider just how transformative this continuous reasoning loop will be for the future of digital work. When an AI can independently, meticulously plan actions, execute tools, and seamlessly course-correct its own errors, we are no longer just prompting a machine. We are delegating work to a digital colleague. So the most provocative question we face now isn't just what complex tasks we'll hand over, but what our own roles will look like once these agents are doing the heavy lifting.